Now we want to talk about the Biot-Savart Law. And the Biot-Savart Law is the general method, or brute force method, if you will, for calculating magnetic fields. And the Biot-Savart Law is somewhat much like the electric field for electric charges, where if you have a charge, you can calculate the electric field from Coulomb's constant times the charge divided by the distance squared in the direction of the line connecting the charge to the field point. And this is an empirical rule. Okay, so we tested this in the laboratory. We didn't derive this from a theoretical consideration. We found Coulomb's law experimentally and then defined the electric field to be equal to the force per unit charge and called that the electric field. It turns out the electric field is a real thing, as we will see, or hopefully have established already, but it does have physical consequences beyond just a static charge. And magnetic fields are much the same way. But the magnetic field calculation is a little bit more involved. It looks a little bit more involved, and you actually do have to carry out an integral here. Now, I should mention, okay, that the Biot-Savart law, once again, is an empirical rule. So this was things that were measured in the laboratory over and over and over again, and looking for patterns and looking how systems behaved, and we were able to find this. And this is going to take a little bit of explaining, okay? So B is the magnetic field. We've already established that magnetism is generated from moving charges or current, right? So anytime you have a magnetic field, that is coming from the generation of current somewhere. Somehow charges are in motion. When you have a circuit like a wire that is carrying current, you can look at a segment of that wire, DL. Okay, so DL is just a segment along the wire. And R hat is the direction between the point on the wire DL that you're calculating the field from and the field point you're calculating the field at, or at which you're calculating the field. And the R vector, R squared, is the magnitude of the distance between those 2 points. So first thing to note, okay, this is a cross product again. So that means that whatever plane DL and R hat end up lying in, the magnetic field is going to be perpendicular to that. So this is a bit of a break from electric fields once again, in that the electric field was either in the direction of the line from the charge to the field point or opposite that direction, depending on the sign of the charge. But here the magnetic field is going to be perpendicular to that. Okay, so the best way to get familiar with the Biot-Savart law is simply to do an explicit example. Okay, so, and we'll go through this equation and how to use it step by step for 2 separate examples. Okay. The first example that we will look at is the straight wire. And if you look at the straight wire, so I have a wire, and let's let this be in the plus x direction. Let's let this be in the minus x direction. So my wire lies in the xy plane, or I'm sorry, along the x-axis. And I want to evaluate the magnetic field at a point, I'll call it P, that is a distance y above the center of the wire. It turns out that you don't really need to be above the center. It does make the integration slightly more symmetric, so it's a little bit easier to do. But in principle, you don't actually have to be over the center of the wire. The Biot-Savart Law doesn't carry the inherent need for symmetry the way that the electric field calculation did with the integral that we did several chapters ago. But the basic way to set it up is this. Let me assume that my current is along the positive x-axis. Okay, so there's my I. And once again, if we come back here, dl will always be in the direction of I. Okay, and once again, I should also stress, like the electric field, the integration that you're going to do here is over the source of the current. So, as a reminder, the integration will always be over the source of your current, whatever that source may be. So, if we look at our wire, okay, now we can, the wire can be of any length. It does not matter, right? The wire does not matter. And why am I grayed out here? Give me just a second. All right, so our wire can be of any length we want, right? So we'll just call it length L. It'll turn out that this isn't imperative for our problem unless you want to set up your integration a specific way. But what here's how to set this problem up. Okay, so the first thing to do is to define your DL. Okay, so your DL is a differential element of current. So I'm going to take a differential element of current, call it DL, and it's going to be along the x direction since my line lies on the x-axis, and as a result, I can just go ahead and say that dl is equal to dx. Okay, and not only that, but this is dx in the x hat direction because the current is pointed toward the positive x-axis. And my r vector is going to be along the line connecting dl and p. So this is my r vector, and r hat is the unit vector that lies along this line, or the vector with a magnitude of 1 that lies along this line. Okay, and remember that all of this is happening in the xy plane, right? All of this is happening in the xy plane. And we can even go a step further and say that this makes an angle theta with respect to the x-axis. R makes an angle of theta with respect to the x-axis, and therefore we might find these relationships useful. X is going to equal r cos theta, y is going to equal r sine theta, and y over x is going to equal r tan theta. Okay, write that out a little bit more cleanly. So r tan theta. And so this is what we have. Okay. Now, we can start by writing out the whole Biot-Savart Law in its glory. And I have not mentioned anything about mu naught yet. And we'll talk about mu naught toward the end of this lecture, but for the moment, okay, for the moment, just note that this is the magnetic equivalent of epsilon naught. Okay, it's called the permeability of free space, and it is a constant that governs the strength of how magnetic fields can propagate through space. Okay, and it plays the magnetic equivalent of epsilon naught to electric fields. And so we're dealing with this cross product portion here. We've got our dl defined, it's dx in the x direction, and r is in the xy plane. So another relationship that might be worth looking at is, remember that r, technically, okay, I really should draw this a little bit more precisely. Technically, r is the vector that stretches all the way. Okay, technically that is r. And if I define my dl to be a distance x from the line connecting P along the y-axis to the current, then r is going to be equal to rx in the x direction plus ry in the y direction. Or if we use, I should use i's and j's and k's. Be consistent with what we've been doing. So this is in the I direction. So r is going to equal rx in the I direction, ry in the j direction. And r hat, okay, r hat is going to be then equal to, oops, I want black. Remember that r hat just has a unit of 1. So r hat has a magnitude of 1, okay? And so r hat you can think of as having a component in the x direction plus a component in the j direction, okay? And these would be such that rx hat would be equal to r hat cos theta, and ry hat would be equal to r hat sine theta, and you would have that the magnitude of r hat, or 1, is equal to the square root of rx squared, rx hat technically plus ry hat squared. Okay. So I know this is a lot, and you won't have to write down all of these relationships for every single Biot-Savart problem, but it won't hurt to get into the habit of thinking through which of these you might need. How, if you have an angle appearing in your problem, how is that angle going to relate to your vector, your r vector? How is your r vector going to be split up amongst your unit vector? How are those components going to work, and so on. So now we are ready to get the DL cross R hat done. Okay, we are ready to get the DL cross R hat done. Now, remember, DL cross R hat is equal to the magnitude of DL times the magnitude of R hat times the sine of the angle between them. Okay, and the magnitude of R hat is just 1, so this just goes to the magnitude of DL times the sine of theta, where theta is the angle between DL and R hat. So that's already what this angle is. So this theta that we've defined is already that angle. So the sine of that angle is going to play a role here. And we've already denoted that the magnitude of DL is just R dx. So DL cross R hat has a magnitude of dx sine theta. Okay. Now, that does not solve the direction. And R hat and DL are not perpendicular to each other, so you can't just use the right-hand rule. Okay. You can't just use the right-hand rule. What you actually have to do, okay, is if you want to be very precise about this, you have to do the matrix. All right. So if we set up that matrix, DL cross R hat is going to equal I, J, K. And my components of DL were dx in the I direction, and I didn't have anything in the J direction or the K direction. And R hat had components in the I and J direction. So what is the determinant of this matrix? So my first term, well, if I look at, I cross out the I column and the first column in the first row, and I look at the resulting matrix. This is 0, so this is 0 in the I direction, and then I get minus. And same thing happens when I cross out the J column and cross out the top row. I get 0 times Rx and 0 times dx. This is 0 in the J direction. And then this is going to be plus, if I cross out the last column in the top row, dx times ry minus 0 in the K direction. So all of the magnetic field appears in the K direction. And by the way, dx times ry is the sine component of r hat. The y component of r hat is the sine component. So this turns into dx times the sine of theta. And so we get the same magnitude that we got using this, but now we have the direction specified. Okay, so now we have the direction specified. So now that we have that, we can look at our integral, and we can say B is equal to mu naught times the current divided by 4 pi. And by the way, the 4 pi is there just for convention in SI units. Okay, the 4 pi is there just for convention in the SI unit system. There's nothing deep about the 4 pi being here. And so then we had DL cross R hat, which turned into dx sine theta divided by R squared. Okay, so now the R squared. Well, R, and right now, we have to decide, okay, am I going to integrate over a length? Am I going to integrate over dx, in which case I need to transform sine theta using these relationships into length values, x, y, and z, or I need to translate all of my x, y, and z values into angular units and integrate over angles. In this case, it's usually standard to integrate over angles. So what we do is we say, okay, I'm going to integrate from some maximum angle, and let's give it purple. So the endpoint is here and the other endpoint is here. So I translate all of my quantities into angles, and I would define this as theta minimum, and I would find this as theta maximum. Well, I actually let me rephrase that. If you're going to integrate this angle, then that would be the angle phi. And I'm sorry, I'm kind of all over the place, but it will actually make more sense to, let's call this phi. Let's call this angle phi. This would be phi minimum, and this would be then phi maximum. So we're integrating an angle from here and then sweeping that angle out this way. You can integrate from sine. This would be sine minimum, and this would be then be sine maximum. If you're going to integrate over theta, okay, this would be theta min, and this would be theta max. But if you define your angle to be phi, then you'd be integrating from here. So it doesn't matter which one you go. You can get there either way. You can use theta from here and keep it that way, or you can find theta and then use trig to find phi. It doesn't matter. But usually the angular form is going to be a little bit easier, as we will see. Okay, so that means we need to transform this R value into variables that I can integrate over, into angles. And which one am I going to want to use? Oh, and by the way, I also need to do something with dx. So let's look at the y value first. Okay. Oops, that r doesn't need to be there. This is the definition of tangent. In looking at my r, okay, when I'm looking at my r, what I don't want to do is introduce extra things that I would then have to integrate over. Our integration is going to be over the x direction, okay? So I don't want to introduce more x's than I have to, because then I would have to do some nasty algebra to get things in a differentiable form. So what I want to do is avoid x's. I want things that have r's and y's, but no x's. So r's and y's but no x's is the sine function. So y is going to equal r sine theta, or r is going to equal y over sine theta. So r is going to equal y over sine theta. And remember, y is a constant. And by the way, we showed that the magnetic field is going to be into the z direction, and in this case, if we define x to the right and positive y upward, then that would be into the board. So my magnetic field is going to be into the screen, okay? All right. Um, and then what we've got, um, my r squared was y over sine squared. 1 over r squared is sine squared over y squared. Okay, so we've got this. And sine times sine squared is just equal to sine cubed. So I can get rid of this. And finally, we need to handle the dx. Well, again, the dx I want to find in terms of things that aren't going to contain x's anymore. So if I use the x equals r cos theta, right, then I could say that dx is equal to d of r cos theta. But notice that as I sweep my angle across my wire, the value of r is going to change, as is the value of theta. So then this would technically be dr cos theta minus r sine theta d theta. And that's nasty. I don't want that. And r depends on x anyway. So you're really taking a differential of something that you're trying to integrate over, and that's just nasty. So we don't want to use that. We want to use things that have constants in them if we can. And that's where this tangent function is going to come in. So when I solve for x, I've got x is equal to y over tangent theta. And when I take the derivative of that, dx, this is going to be y times the cosecant squared of theta d theta, right? And so this takes care of dx, and I can plug my dx in, and this is going to be equal to 4 or mu naught I over 4 pi, and integrate dx, we just said, is going to be y times cosecant squared, but cosecant is 1 over sine. So this is going to be y over sine squared theta. This is the cosecant part. Sine cubed theta over y squared d theta. And the y squared cancels with the y, and I'm left with a y in the denominator. And sine cubed cancels with both of the sine squareds, and I'm left with a sine in the numerator. And now all I need are the limits, right? Now all I need are the limits. And the limits are going to be those theta min and theta max, right? Whatever the case may be. So theta min, and we'll use this angle. So I'm going to integrate from here and then sweep across until I reach this angle theta max. And so this equals mu naught I over 4 pi times, y is a constant, so it can come out of the integral, times the sine of theta from theta min to theta max. Okay. And then this is mu naught I over 4 pi y. And the result is negative cos of, okay, but notice, all right, so if you want to be very brute force-ish about this turns into, and by the way, this is all in the k direction. Right? And so if you want to be very brute force-ish about this, it would be mu naught I over 4 pi y times negative cos of theta min minus negative cos of theta max. I'm sorry, this is negative max minus the cos of theta min. Okay, so this is mu naught I over 4 pi y, and this is now cos theta min, minus cos theta max. But, okay, we can write this in a slightly cleaner way. If I want to use this angle right here, okay, if I want to use that angle right there, we can call this angle whatever we want. Let's call this angle gamma, okay? Gamma and theta max are related by they're supplementary. So 180 minus theta max equals gamma, okay? And what that means is that the cos of theta max is minus the cos of gamma, okay? The cos of theta max is minus the cos of gamma. And as a result, what we get here is the cos of the minimum angle plus the cos of the inner angle at the maximum value. So I'm not really integrating from here to here. I'm integrating from here to here and then using geometry to transform the cosine of this angle into the cosine of this angle. Okay. And as a result, this is what we get. And this doesn't necessarily look very pretty, but if you can measure those angles, then this is a relatively simple formula to use. Okay, this is relatively straightforward. I know that that was probably enough to make your head spin. So we will actually leave this lesson there minus a short discussion on mu naught, and then we'll save the second example for the next video. So mu naught is called the permeability of free space. Okay. And it's defined as the units or a value. It has the value defined to be 4 pi times 10 to the negative 7. And this is where the 4 pi comes in the Biot-Savart Law. to make that coefficient effectively 1 times 10 to the negative 7. And the units aren't necessarily intuitive to see, okay? The units aren't necessarily intuitive to see, but if we look at this, we know that the field is in Teslas. We want to find the units on mu. The current is in amps. And we have a distance divided by a distance squared, the integral of 1 over meters, right? The integral of 1 over meters. And this may or may not be useful. But the end result, okay, the end result is that the units on mu are Teslas, are Teslas times meters per amp. Okay. Teslas times meters per amp is what the units on mu are. Okay. And as a result, Teslas times meters per amp. This basically gives the or defines the strength with which B fields can propagate through space. And that's all there is to it. It is, again, the magnetic equivalent of epsilon naught. And in fact, these two quantities, mu naught and epsilon naught, are actually intimately tied with each other in a very deep way. So when we get to light, we will see that connection a little bit more clearly. Okay. I apologize for the seemingly slightly random behavior going back and forth. The Biot-Savart Law is not the easiest thing to set up every time. And so I would encourage you to go back through and watch the video a couple of times and really try to digest what we're doing. The basic recipe is define DL, okay? Define DL according to your current, and find R hat and its components to take the cross product with to get your direction. And then define the integration variable you want to use, whether you want to stay in Cartesian coordinates or if you want to move to angular coordinates. And then translate all of your variables into that set of coordinates and then carry out the integration. Okay. I know easier said than done, but that is the general recipe. And note, okay, we should note this, that the form of the magnetic field that we arrived at is dependent on 1 over the y. And this is partially the dipole feature. Okay, this is partially the dipole feature. And where's the dipole that we're talking about? Well, if I looked at a spot on the negative y-axis and I do the exact same calculation, I would find that below the axis, it's going into the page. So the magnetic field above the axis is coming out of the page. If I said into the screen earlier, I meant out. This is out of the screen. And below, it's into the screen. And notice that this is true for everywhere above the wire. It wouldn't matter where I tried to measure this field. It would be out of the screen coming at me above the wire, and it would be into the screen everywhere below the wire. So what this means is when we look at a wire and we're looking at the two-dimensional projection of the magnetic field, we're actually seeing slices of a circle. And those circles are wrapping around the wire. And those circles have a specific direction. So when I look above the wire, in one case, if my magnetic fields are wrapping around this way, when I look above the wire here and here, I would see into the page. And when I look down here, I would see coming toward me out of the page. But in reality, they're really wrapping around. So the moral of this story is that the magnetic fields of a circular wire, or I'm sorry, magnetic fields of a straight wire, form circles around the wire. If I wanted to measure a closer radius than this, then I would draw another circle, and that circle would have a stronger field than the outer circle, right? The closer you get to the wire, the stronger it gets. That's the 1/r dependence. And so that is the Biot-Savart law for a single wire. And if you wanted to stretch this out to an infinite line, okay? So if you have a really long line and you want to stretch this out, I'll let you think about what your limits of integration ought to be, okay, in an angular sense. Um, so with that, I hope that things make some sense, and we will see you in the next video where we will talk about the magnetic field of a circular loop of wire. All right, we'll see you then.